Hi everyone. I hope you had a good weekend and that things are still going well. We are kicking off into our discussion on the Laplace transform, and in order to set the stage for that, I want to have a little bit of a background discussion on differential equations. This discussion is going to assume that you don't have a large amount of knowledge about differential equations, but it's also not intended to be a rigorous, in-depth, full education on differential equations either. It's essentially just to set the stage for what they are and try to give you some insight into them so that we can deal with them when we discuss Laplace transforms and system input-output relationships and things like that. So the first thing you might ask is, what is a differential equation? It's going to be an equation that relates a function and its derivatives. So essentially any equation that contains a derivative can be thought of as a differential equation. But for our purposes, we're going to deal with ordinary differential equations. It's essentially going to be a function of a single variable. So we'll have something like y equals f of x. Okay, so that shouldn't be a surprising construct to you in terms of functional relationship. When we talk about the derivative of y, or the derivative of f of x, right, y is going to vary typically as x varies. So how do we write the derivative? Well, you're probably familiar with several different representations of the derivative. So for example, you might see y dot with a dot over it, that's the first derivative, or you might see y prime, instead of a dot it's like an apostrophe, and a single mark there again means the first derivative, and that's what we're going to focus on for our discussion here in this session. You also might see it written as f prime of x, so that denotes more clearly the functional representation. And another way to write it might also be something like dy over dx, where we actually write out what we might call the differentials. All of those are valid notations for what we're going to be doing, and it really depends on what we're doing. Sometimes it's just purely for shorthand. Other times there's a meaning to why we're going to break it up a particular way. All right, so just keep that in mind, that all of those are valid notations for the most part for what we're going to be doing. The order of a differential equation, the order is basically governed by the highest derivative that is in the equation. So for example, a differential equation with only first derivative in it would be a first order differential equation. One with the third derivative in it would be a third order differential equation. So as an example, for first order, we would have something like, for example, y dot, or y prime if you want to call it, that y dot minus xy equals 0. That is a first order differential equation. A second order differential equation might be something that looks like 2y double dot, so that's a second derivative, minus 3y dot, so that's 3 times the first derivative, plus x, right? Remember, y depends on x, and let's say that equals 5. So that is a second order differential equation. Okay, so we can write a lot of differential equations, but really what we want to do is focus on the solution to the differential equation. And so what is the solution to the differential equation? Well, essentially the solution is that function y equals f of x that satisfies the particular differential equation that we're talking about. So again, recall y equals f of x, right? No magic there. And let's look at a simple differential equation. Let's look at y dot minus x equals 0. That's a simple first order linear differential equation, and we'll talk a little bit more about the linearity concept in a moment. It's first order though because it has only a first derivative in it. Now I can write this in a slightly different form. I can just take x to the other side, and say y dot, or y prime, if you want to write it that way, equals x. Okay, so that's not very earth-shattering relationship to be able to arrive at that from what we were first given. And I really want to say, what does that mean then? I'm looking for the function y that satisfies the condition that the derivative of y equals f of x equals x. Okay, so y prime equals x. I could also, right, instead of y prime or y dot, I could write f prime of x, if that makes you feel better, right? So I'm looking for the function f of x whose derivative is equal to x. So what function do you think might satisfy that? What is a function whose derivative is x? Well, I can think of one that's pretty straightforward. It would be y equals 1/2 x squared. Okay, so think about that. If I take the derivative of y, I'm going to take the derivative of 1/2 x squared. It's just sort of a polynomial derivative type concept, right? So that derivative, right, y dot equals, right, I have my 1/2, and I'm going to bring down the 2, and I have x, right? So that just equals x. So I do have a function, y equals f of x, whose derivative, f prime of x, equals x. So I actually have a solution to the differential equation. So this is my solution. Now I can go a little bit further than that, because I could actually talk about a more general solution that might look something like y equals 1/2 x squared plus some constant c, right? Because if I take the derivative of that, I'm still going to be left with x, right? So I know that y dot equals x. This constant, all that does is shift this function y up and down, but the slope is essentially still the same everywhere. So what this is this is a general, so this is a general solution to this differential equation. So really what we have are infinitely many solutions to the given differential equation. They're all separated by different values of the constant c. All right, so I've rewritten the simple differential equation again with its solution. So again, the differential equation, y prime minus x equals 0, and the solution, the general solution, is y equals 1/2 x squared plus c. Okay, so suppose I'm given some additional information that says y of 0 equals 3. Okay, so if I have that information. Now this notation here I'm using is sort of a mix of the functional notation and the using of y, but I think you understand what that means, and it's generally okay. So this y of 0 equals 3, well, what that means is if I plug in x equals 0 into this equation over here, I should get 3. Okay, so if I plug in x equals 0, then I know that this term here, this entire term, is going to be 0. So what that tells me is y equals, let me write it this way, y of 0 equals 1/2 times 0 squared plus c, and that equals 3. Well, I can tell pretty obviously that that means that c equals 3. So now, because I have created this constraint here, this initial condition, it tells me something about how the function starts out at x equals 0, then I have now constrained that to be a particular solution to the differential equation. So now I know that my particular solution, instead of a general solution, is given by y equals 1/2 x squared plus 3. If I take the derivative of that, I still get x. So it still satisfies the initial differential equation, and that always must happen. Now, a first-order differential equation is called linear if it can be written in a particular form. Okay, so we have a linear first-order differential equation. It can be written in the form y dot plus p of x onto y equals q of x. Okay, so now all of a sudden there's a lot more going on here. But really this isn't very scary. So what we have here is we have, again, the first derivative of y, and we have y itself here. So y appears at most at the first as a first derivative, so this is a first order differential equation. And then I have these other terms here. So I've got this p of x here and q of x over here. Those functions p and q are functions of x, but they could actually be constant, right? So you could have a function of x that's just constant for all x, and that doesn't violate anything. So p of x and q of x are functions of x. They don't have to be the same. Matter of fact, they rarely are. If the total equation can be written in this form, it's known as linear. Let me clarify just a little bit. I want p of x is some function of x. And that's possibly constant. And q of x is also some function of x. The first derivative of y plus y times some function of x equals some other function of x. And in that form, we can tell that it is a linear first-order differential equation. Okay, sometimes you may hear the term ordinary differential equation. Ordinary differential equation, or sometimes it's just called an ODE. Okay, an ODE, or ordinary differential equation, is just what we've been talking about. It's because we have a function of a single variable. If we get into multivariable functions, like functions of x and y and z, then we start talking about these things called partial derivatives and partial differential equations, and those are outside of the scope of what we want to deal with. So everything here is going to be an ordinary differential equation. Okay, so it involves functions of a single variable. And again, that's like y equals f of x. Okay, so there's should be no surprise there. All right, so let's look at some examples of our ordinary differential equations when we're going to talk about linear and nonlinear. Okay, so as an example, let's consider y dot plus xy equals negative x squared. Is that a linear differential equation? Well, if we look at p of x equals x and q of x equals negative x squared, then we see that these match our definition, right? So there's the q of x and there's the p of x. So they don't have to be complicated functions of x. They just have to be functions of x. So this is a linear first-order differential equation. Let's do something like y dot plus xy squared equals negative 5. Okay, well, I'm still okay for this to be a function of x. Even though it's constant, it still can be described as a function of x. And this is still a function of x, just like what we had in the previous example. But notice that it is not multiplying just a y. It's actually multiplying y squared, right? So this one is going to be a nonlinear equation. So it doesn't match our form. We have a p of x and a q of x, but we don't have a y dot plus p of x onto y equals q of x. We have a y squared here, which causes a problem for us. So that makes it a nonlinear differential equation. Let's look at another example. Let's look at y dot minus x squared y equals 0. What do we think of that? Well, we have a condition here that p of x equals negative x squared, and we have q of x equals 0, which is, again, a boring constant function of x, but it still satisfies our structure, so it is going to be a linear differential equation. Guess I didn't mark this one up here. This one's also linear. All right, so those are both linear differential equations. This one here is actually also called homogeneous. Or homogeneous, some people might call it. I tend to go back and forth, I guess. Most of the time I think I use the term homogeneous. By the way, if you've studied differential equations, you probably may understand that the term homogeneous or homogeneous is used in two different ways regarding differential equations. And our definition of homogeneous is going to mean this. It's going to mean simply q of x equals 0 for a linear first order differential equation. Q of x equals 0. Essentially means the right hand side is 0, and we're going to call that a homogeneous differential equation. We're going to expand on that a little bit when we get to second order differential equations, not in a real big way, but just keep that in mind. Okay, so this first equation up here, this is not homogeneous or not homogeneous, and neither is the second, but the third is a homogeneous linear first order ordinary differential equation. So there's a lot of things we got packed into that, but hopefully now it's starting to become a little bit clear to you. Okay, so we're going to talk for just a moment about solution techniques, and only to the extent to say that there are many different techniques, and they depend largely on what the structure of the particular differential equation is. This is not a differential equation course, so my goal is to not teach you a bunch of different techniques, but only to make you aware that they do exist. We actually implicitly used a solution technique when we talked about our earlier differential equation that looked like y prime minus x equals 0, right? We wanted and we did it by finding a function. We just thought about it for a moment and determined, well, I can come up with a function a function of x whose derivative is equal to x, right? Because I could write it also this way, y prime equals x. By inspection, we knew it had to be something that looked like y equals 1/2 x squared plus some constant c, and that it was our general solution to that differential equation. So again, we could do that kind of by inspection. So now let's use that concept with a different example. What about y dot minus y equals 0, right? I'm not using x anymore, I'm using y. Well, first of all, what can we say about that equation? It still has the same structure as a linear first order, and this is actually a linear first order homogeneous differential equation. The q and the p functions are both kind of boring. Q is 0. That's what makes it homogeneous, and p happens to be just -1, right? So it's constant. But anyway, so I have something here that now, instead of what I had up here, right, I was looking for a function whose derivative looked like x. So I wanted a function of x whose derivative looked like x, and we know that we had this general solution. So in this case now I want a function whose derivative looks like the function that I started with, right? Because I can write this in a little bit different way. I can say y prime equals y. So that means I want a function y that looks like its derivative. And this one may make me think a little bit longer, but I can still just basically guess at a solution and maybe use a little bit of intuition and then check to see that it holds or not. Okay, so what I'm going to do is quote unquote guess and say, well, I'm going to choose y equals e to the x. All right, so what does y prime look like? Well, it's no surprise that, or y dot, right, that's going to be e to the x. So clearly this function here satisfies this differential equation. And so just by inspection, I said, well, I'm going to try e to the x, and lo and behold, it actually worked. All right, so you're going to find that that kind of intuition can be used in a lot of cases. Now, I want to think about just for a second, what about generalizing this and say, well, I want to use y equals e to the x plus c. Well, what is the derivative of that? Well, the derivative is e to the x, but it doesn't hold, it doesn't match our differential equation because I need to have that constant on both sides, and I wouldn't have that. So I can't say this is a general form solution, and you got to be careful about that. There are times when that works well, and there are times when you want to be careful about it. Okay, let's look at another example. Let's look at one where we have y dot minus 3y equals 0. So there I want to think about what function do we have, right? I want to find y such that y dot equals 3y. So I want a function whose derivative is 3 times the function that I started with. And I can say, well, let's try y equals e to the 3x. What is the derivative of that? Well, the derivative, y prime, equals 3e to the 3x, which equals 3y, 3 times the original function y, right? I take this and I can insert it right there. So again, by just thinking about that a little bit, I could say, well, I can develop a solution that fits. And taking that one step further, actually, I can say for the general form y dot minus ay equals 0, then I can say the solution is going to be y equals e to the ax, where a is just a scalar real number. Okay, so let's take this a little bit further, and I'm going to adjust my notation slightly just to support a little bit of what I want to talk about. But I'm going to say, let's say we have the equation y dot of t. Okay, so now we have a function y that's a function of time instead of x. And it doesn't really matter, but what our notation is. But we do find that we talk about functions of time a lot in this course, so I thought I would go ahead and stick that in here. So I have y dot of t plus a onto y of t equals b onto u of t. Okay, so let's think of that differential equation. And here, it's important, u of t is actually something specific, and it's going to be our unit step function, right? So u of t actually looks like 1 for t greater than or equal to 0, and 0 otherwise, or for t less than 0. Okay, so that's our unit step. You may recall that from circuits 1. Okay, that's our unit step, or sometimes we just call it a step function. And what I'm doing here is allowing the unit step to be scaled by some scalar value b. Okay, so I'm just putting in that in there for a little bit of generality. Okay, and then I also have a scalar over here, a. So now if I think about that in terms of my original form that I had for a linear differential equation, does this match? And the answer is Yes, it matches because I have what we're going to say is P of t, right? Instead of x, we're using t, is a, and Q of t equals b onto U of t. Now, why am I bothering to bring it up this way? Well, this is going to be a particular solution technique that I want you to pick up on just a little bit. Okay, so first we're going to define something called the integrating factor. Okay, this sounds complicated, right? But don't let it worry you. Okay, so we're going to say the integrating factor. The integrating factor well, that's going to be I of t. I'm just going to refer to it like that. And it's going to be equal to e raised to the exponent, and the exponent is going to be the integral of P of t dt. Okay, so that again may look complicated or scary, and it can be computationally for complicated problems, but we're not going to go that far here. But I do want to bring up some useful things to note about that given this structure. So this I of t is the integrating factor, and it's just e to the integral P of t dt, right? And our P of t is this expression here. For our case, so just what we're talking about here, we have I of t equals e to the integral of a dt, which is just going to be e to the at. Okay, so it's not really that scary. Now, what happens if we multiply both sides of our original differential equation by the integrating factor? So essentially, I am going to take I of t, and I'm going to multiply by the original differential equation, right? So I had y dot of t plus a y of t, and that's going to be equal to I of t times b u of t. So I'm going to have e to the at y dot of t plus a e to the at y of t, and that's going to equal, and I'll just use a different color for the other side, that's going to equal b e to the at u of t. All right, so that seems maybe a little bit more complicated, but it'll be interesting what we can do with it. Okay, so I want to point out something interesting about the left-hand side here. Okay, so first of all, think about this for just a second. If I had I of t times y of t, okay, so my integrating factor times the function that I'm looking for, and I compute the derivative of that with respect to time. Okay, the derivative d dt. Well, I've got to use the chain rule, right? So if I do that, I've got to take the first expression times the derivative of the second plus the derivative of the first times the second. Well, what do I have? What do I get when I do that? Okay, so I'm going to say that's going to be equal to the first expression times the derivative of the second. So it's going to be I of t times y dot of t, and then plus the derivative of the first expression, which is I dot of t times y of t. Okay, that's what the chain rule gives me. Now, if I plug in the expressions that I had for my example, right, we're going to see that if I just write those expressions down here, so I of t, right, the integrating factor was just e to the at, and then here we just bring down our y dot of t, and then plus, and then over here we have I dot. So I've got the derivative of e to the at. Well, that's just going to look like a e to the at, And then again, I just bring down y of t. So presuming I said all that right, I've got e to the at times y dot plus a e to the at times y. And if you notice, that's what this expression is. So I can write the left-hand side of this equation as just the derivative of the integrating factor times y of t. So why do I care to do that? Well, I want to do that because I want to be able to integrate that derivative and just get I of t times y of t, and you'll see why in just a second. What I have here, by doing what I did, is I have the derivative with respect to time, I'll just write it this way, of I of t times y of t equals the derivative, and I'm going to plug in the values for a particular example because that's what I need to do on the right hand side. So that's going to be the derivative with respect to time of e to the at y of t, and that's going to equal b e to the at times u of t. So now that I have this, I can integrate effectively both sides of the equation. And sometimes what we'll do is we'll take a little liberty with this dt in the denominator. Okay, so I'm going to write this with a little bit more precision when we can manipulate the differential terms, but don't worry too much about it. So what I'm going to have is, by taking dt to the other side, I'm going to have the differential I of t. Well, let me use our actual example. So what I'm going to have is a differential of e to the at onto y of t equals b e to the at u of t dt. And then I can integrate both of those. So I can take the integral of each of those. Okay, so if I do these integrations, then what I'm going to have is I'm just integrating a differential of this expression. So I'm just on the left-hand side, I'm going to get e to the at times y of t. And that's going to equal, well, over here, b is a constant, so I can pull it out of the integral. U of t is just 0 when t is less than 0 and 1 otherwise. So I can just practically, for my integration purposes here, pretend it's not there. And so I'm really going to have something that looks like b times the integral of e to the at dt. And that's going to give me b over a e to the at plus some constant k of integration. Okay, so now I can just divide e to the at out of both sides. On the left-hand side, I just get rid of it, so I'm just going to end up with y of t, and that's going to equal, on the right-hand side, I've got this term here. Well, I'm just going to divide it by e to the at, so it goes away. So I get b over a, and then I have plus k divided by e to the at. Okay, which I can write that a little differently. So I can write it as b over a plus k e to the minus at. That way I keep it in the numerator. Okay, so now I want to go one step further. I have a form here, but this k is an unknown value. So now, oftentimes our problems that we're going to assume 0 initial conditions. So we're going to assume a function value is 0 at time 0. So I'm going to presume here that y of 0 equals 0. And that's just going to equal b over a plus k, right? Because e to the 0 power, e to the something to the 0, e to the 0 power, right, is just going to be a 1, right? So I just have that expression. And since this has to be equal to 0, that tells me that k equals negative b over a. And from there, I can now rewrite the solution to the differential equation, given those initial condition constraints given by this, I can write y of t equals b over a minus b over a e to the minus at, and I can shorten that a little bit more, saying, well, it's just going to be b over a times the quantity 1 minus e to the minus at. Okay, so what can we do with this information? Well, let's go back and look at our simple RC low-pass filter circuit, right? So if you recall, the filter looked something like a resistor, and we had a capacitor, right? And this is what we called our two-port network. So we had the resistor R, we had a capacitor C, and we talked about an input voltage over here, and we talked about an output voltage over here. Okay. So again, we've talked about this a number of times. And we also talked about how I can write the equation for this. And so I can say, well, I know that the current, right, if I think about the current that's going to flow here and like that, right, so I can call that I of t, right? It's not going to flow out these terminals at V out because V out's not plugged into anything. So we're just sort of analyzing the circuit in some sort of isolated fashion. But because I know I can write a current equation, I can say, well, that VI of t minus V out of t over R equals I of t. So that's my current. And I also know, because of the capacitor relationship, that I have the current I of t is C dV out of t dt. Okay, so obviously both of those expressions must be equal. And so given that, I can just write it in one big long expression. I can say VI of t minus V out of t over R equals C dV out of t dt. Okay, I can do some rearranging, and I can say Vn of t over R minus V out of t over R equals C V out dot of t. I'm going to, instead of writing the derivative the way I did before, I'm just going to write it with a dot. So I can rearrange a little bit and divide through by C, and I'll get V out dot of t plus 1 over RC V out of t equals 1 over RC Vn of t. Okay, so this is a linear first order differential equation, ordinary differential equation, that describes the input-output characteristics of this first order low-pass filter. Okay, let's compare this to the expression that we had in just a few moments ago in the earlier part of our discussion, where we had y dot of t plus a y of t equals b u of t, right? So what I had there, right, I have y of t is my output, and y dot of t is the derivative. So I have a correspondence here. So this expression here matches what I had for my my circuit under the conditions that A equals B equals 1 over RC, right? And also that VI of t equals U of t. So if we think about our first order circuit, our low pass filter circuit, let's assume for a second that we have 0 voltage on the capacitor, and then we attach an input that's just a step voltage input. So the voltage just at t equals 0 transitions from 0 to 1. It's not a sinusoidal expression or anything like that. Well, we've already got the mechanics worked out that we can describe what that solution is going to be. Okay, so presuming that we have these conditions right here, then I already can write down the solution that V out of t for our differential equation V out of t for our circuit, I should say, is equal to 1 minus e to the minus t over RC volts. And if I were to plot that as a function of time, this is probably no surprise to you. And let's make this a 1. So if I were to plot that as a function of time, it's going to start at 0, and it's going to rise and asymptotically go toward 1 volt. Okay, so I should finish labeling over here. So this is going to be voltage. In particular, V out of t. All right, so I have a mathematical model I built strictly using differential equations to describe the input-output behavior of our circuit. And I know we've kind of talked through some of this a little bit in class before, but I wanted to dig into the differential equation nature. Now, what's happening here? Well, this circuit, we were saying we're just inputting a step input to it. Okay, so that's cool that we can work this out, but now what happens if we have more complicated inputs to the circuit? Okay, so for this circuit, let's suppose that Vi of t equals cosine omega t. Now we're still going to operate under the assumption that we have zero initial condition, which means that the capacitor is not charged at all. So we're going to have a transient before we reach sinusoidal steady state condition. All right, so let's think about what happens here. First of all, let's go ahead and write the differential equation describing this. So we're going to say, well, we're going to have V out dot of t. And I'm going to go ahead and just go ahead and say we're going to have this 1 over RC times V out of t. And that's going to equal 1 over RC times cosine of omega t. Okay, so now just to keep ourselves sane here, let's think about this a little bit. So this whole expression over here is my Q of t expression. Okay, so it's a little more complicated, and but P of t is just a constant 1 over RC. Okay, so now if I want to build my integrating factor, I of t is just e to the integral P of t dt. And so that's just going to be e to the t over RC. Okay, so we could work that out again, but I think you can handle that. Okay, so now I can take a little bit of a shortcut with what I know. So generically, we had something that looked like y of t times the integrating factor should equal the integral of q of t times the integrating factor dt. Okay, so if we apply this to our specific problem at hand, we're going to get something that looks like V out of t onto e to the t over RC equals the integral of 1 over RC times cosine of omega t times e to the t over RC dt. All right, so you might think that that integral on the right takes a little bit of work, and you'd be correct, but it is something that you can persevere through. But we're not going to dig into those details here for our discussion. We're just going to try to get to the punchline here. So what I'll do is I'll just go ahead and write out what the right-hand side ends up being. Okay, so I'm just going to give myself a little bit more room to do this. So the right-hand side is going to become 1 over RC onto something that looks like e to the t over RC divided by the quantity 1 over RC squared plus omega squared. And all of that is going to be onto 1 over RC times the cosine of omega t plus omega times the sine of omega t, and then all of that plus our integrating constant k. Okay, so that's the solution to the right-hand side integral. So now what I'm going to do is I'm going to divide through by our e to the t over rc on the right-hand side. So I'm going to divide this term out, and I will end up with v out of t equals 1 over rc divided by 1 over rc squared plus omega squared onto 1 over rc cosine omega t plus omega times the sine of omega t, and then plus k e to the minus t over rc. Right, so we saw that action before where we end up with this coming from the denominator to the numerator, and we flip the sign on the exponent. Okay, so now we're going to talk about our initial conditions, right? That we're going to say, well, v naught or v out of t of 0 equals 0, and that's going to equal, so what happens for t equals 0? Well, we know that this expression is going to go to 1, this expression is going to go to 0, right? And then this part of the expression is going to go to 1, so we're just going to be left with a k. So we're going to see something that looks like 1 over rc divided by 1 over rc quantity squared plus omega squared onto 1 over rc plus k equals 0. And all of that is going to lead to k equals negative 1 over rc quantity squared divided by 1 over rc quantity squared plus omega squared. All right, so again, there's a lot going on there, but it's actually not too bad if you work your way through it and just be careful. So we can collect our terms in a little bit more convenient fashion, and we're going to get the output voltage is V out of t equals 1 over RC quantity squared divided by 1 over RC squared again plus omega squared onto cosine omega t plus omega RC sine omega t, and then minus e to the minus t over RC volts. So that's what our expression is going to be. Let me wrap that a little better on that end. All right, so a lot of work. This does include the transient, right? So you might think this thing here that decays is going to have something to do with the transient. And obviously we got some sinusoidal terms in here. So we're going to end up eventually in a sinusoidal steady state condition because we're driving it with a sinusoidal steady state. The fact that we have, I'll make another point here, we have these independent cosine and sine terms with different amplitudes. It turns out when you add those together with different amplitudes, you're going to end up with something that can modulate the phase of the input voltage, because we know that for different frequencies we're going to get a modification of the amplitude and phase of the input to drive the output. And that's actually all built into this time domain response that we have. So the takeaway from all this is that computing these responses can be somewhat involved. Obviously, I spared you the pain of dragging through that integral for the cosine times the exponential. And this was just for, again, it was a sinusoidal input. So imagine if I had more and more complicated inputs. It turns out that the calculations are going to get much more difficult, time-consuming, tedious, and it's just not a lot of fun. So where we're headed is this Laplace transform thing is going to allow us to handle these kinds of situations in an organized and structured manner. It doesn't come without any pain, but at least in this kind of scenario, we should be able to do better. So again, we're going to talk a little bit more about differential equations in our next segment. But again, this is to set the stage to make the reasoning behind. Actually, it's for two reasons. One is to set the stage for the Laplace transform, why we're doing it, but also to give you hopefully a little more insight, if you don't have it already, into differential equations and their nature, especially as we deal with them for our types of circuit models and things like that. So thanks for listening. Have a good day, and we'll be back with the next segment soon.